Hey guys, and welcome to the final video of the topic 11 review series. We're going to talk about topic 11.1, clear up a couple of last minute things, but this should be regarded as a video that is meant to go along with the topic 11.1 material and not to replace it. It's also not a comprehensive review of topic 11.1. Please use the previous posted video on topic 11.1 to provide that comprehensive review. Let's go ahead and get started. So when we talk about the immune system in the body, we often talk about the lymphatic system. We talked a lot about the circulatory system actually because we talked about the delivery of blood, but the lymphatic system works together with the circulatory system. As we can see here on the right, it is connecting with it. And the lymphatic system is going to connect a bunch of lymph nodes around your body. It's essentially going to be producing lymph, which is a clear fluid that contains white blood cells in a liquid filtrate. And that, if you remember, white blood cells are going to be full of those lymphocytes. So remember, those lymphocytes are going to be some of those blood cells that are going to come in and start to attack invading pathogens, very much like macrophages do. And they're going to help your immune response. So the lymphatic system is where a lot of this stuff is going to meet your circulatory system, and they kind of bounce back and forth. It's going to filter out any pathogens that are within the lymph, and it's going to keep pumping your bloodstream full of white blood cells and other types of defender cells to make sure that you are kept safe. So when we talk about the immune system, we are really talking about the interaction between the lymphatic and circulatory systems of your bodies. This leads to several different immune pathways. The immune pathway that you guys learned about when I talked about 11.1 was the humoral immunity. So we have macrophages that present antigens from pathogens on their surface. We have the helper T cells come. They release those wonderful hormones, the cytokines, to go ahead and activate the B cells. The B cells differentiate into plasma and memory cells, and they produce a bunch of antibodies that flood the bloodstream and thus help to defend against invasion. But there is also cell-mediated immunity. So what happens when a cell is completely taken over by a pathogen? What does the body do? That cell has been compromised. That's where we get into cell-related or cell-mediated immunity. Basically, if a cell becomes cancerous or if it is viral infected, then it will display antigens on its surface, kind of like a macrophage. But this time, when helper T cells come, they're going to activate cytotoxic T cells or TC cells instead of the B cells we would expect in the humoral response. The cytotoxic T cells are going to bind to the cells that are showing these particular antigens using something called the death ligand, and they're going to release enzymes that cause those cells to be lysed and destroyed. So instead of trying to just fight off the pathogens, the cell-mediated immunity is where we just destroy cells that have fallen to the enemy pathogen, which is pretty interesting. And I think that response is pretty great because it allows for sort of a macro response, whereas the humoral response is sort of micro. Okay, and then we have types of immunity. So we talked about active immunity, which we talked about both natural and artificial. Natural active immunity is producing antibodies, so it's like the humoral response. And artificial is when we have a vaccine inserted into us that initiates that response. We've already learned about that. Passive immunity is basically where you get any other type of immunity through either your food, like you get it from another organism that you've ingested, or through, like your mother's milk when you're feeding, or artificial. So artificial is going to be when you get a blood transfusion from somebody else, or monoclonal antibodies, which is the next thing we're going to talk about after we talk about immune disorders and stuff. But basically when you get stuff from other people. So here's this wonderful, I guess, chart to show you that, right? So active, infection or vaccination, passive, maternal, or monoclonal. And we'll go into more detail about monoclonal antibodies in just a minute. But those are the big divisions. Immune disorders, we talked about allergens. We said that they acted very much like pathogens and they evoked a very similar response, but instead of evoking so many antibodies created, they actually create inflammation around the surrounding area. So hypersensitivity is when you have a disproportionate immune response to an allergen. So that's when you have what we call bad allergies. And this is because of prior exposure to those allergens. Your body's treating them like pathogens, and we've already talked about that. We have these very localized hypersensitive conditions where we have this swelling because our blood vessels become more porous, and the fluids that are released from the porous blood vessels are entering the surrounding tissues, and they're causing inflammation and swelling, which of course squishes our neurons, and we feel pain. Those achy little fevery kind of feelings you get with certain really bad allergies. And of course, anaphylaxis, which is that very severe swelling of tissue, maybe around your throat, that closes your air pipes and makes it very difficult to breathe. Autoimmune disorders are where those MHC, those histocompatibility complexes, they are misinterpreted. And instead of saying, hey, I'm part of the body, they're like, I'm part of the body. And your body's like, no, you're not. And so your body starts literally destroying itself. And sometimes this can happen because pathogens are actually trying to act like your cells. And so they kind of, I talked about this before, they kind of, the receptors look like the right ones. And they're like, I'm supposed to be here. And your cell's like, When your cells start being like, we have intruders that are dressed like our own, they start killing not only the pathogens that are invading, but sometimes also the real deal, the real cells that are dressed up like real cells because they are. They did nothing wrong. The body destroys them anyway. So this can be a very bad thing as well. So diabetes is an example. Diabetes type 1 is an example of an autoimmune disease, and rheumatoid arthritis and sclerosis. So all very fun, painful things as your body starts to rip itself apart from the inside. Then we have immunodeficiency orders, and the most common one that you've heard about is AIDS. So it can be caused by pathogens, or it can be inherited. And sometimes you'll also have drugs which cause this as well, and those drugs are usually made to make it so your body will reject new stuff that's coming in. Regardless, immunodeficiency disorders are really, really bad because they're going to shut down your body's defense system and leave you open and susceptible to pathogenic attack. Here we have a fun little diagram, I guess, of normal immune functions like a good functioning dog. Hypersensitivity disorder is like, dog, holy God, why are you attacking me? I am your friend. Immunodeficiency disorder is like, the dog is dead. And autoimmune disorders is where the dog is going to fail to detect that you are the person that is supposed to be the good guy, and it's going to attack you. What's the difference between autoimmune disorder and hypersensitivity? Autoimmune starts attacking your own cells. Hypersensitivity is not attacking your own cells, but it is going to be that your cells are going to start treating allergens like pathogens and evoke an immune response. So it's not attacking your own cells, it's just creating an immune response to a threat that isn't there. Whereas autoimmune disorders is looking at your cells and thinking, hey, that's a pathogen, and attacking them, so that's bad. So various of these can be variously dangerous depending on how bad you have them. Finally, we have monoclonal antibodies. So we talked about use of vaccines in order to protect you against pathogens, but there's also monoclonal antibodies. Basically, the idea of this is that you take the antigens for whatever pathogen you want to defend against, and you actually you induce the creation of plasma cells within an organism. So you inject the antigen into the mouse, the helper T cells create the B cells that lead to plasma cells, and then you actually you fuse the plasma cells with tumor cells, which are cancerous and don't stop reproducing, so you can, they reproduce forever, and you create these hybridoma, which are these plasma cells that are now cancerous and can grow forever, and they produce basically endless amounts of whatever antibody that you wanted to make against the pathogen. That's what we call a monoclonal antibody, because they're all clones of each other based off of this rapid mitotic division due to the tumor cell nature of these hybridoma. So this is a really great way of producing a lot of antibodies. Why would you want to produce a lot of antibodies? Well, remember that antibodies are really important in helping to fight off pathogens in your body. They mark them for destruction and are basically the front lines of your immune response. So if you happen to get something like rabies, it can be really useful to inject somebody who has gotten rabies and is suffering from it with a ton of antibodies. It's not a permanent cure because remember, antibodies don't create memory B cells or any other B cells, but they can get in there and start marking the proper pathogens for destruction. Now, we can make monoclonal antibodies in various different organisms. We tend to like to use mice because mice, inserting cancer cells into mice, we don't feel bad about. But the problem is that if we insert them into mice, obviously the mice are going to create slightly different cells from human cells. And so they're going to have various, depending on what types of cells we take from the mouse and depending on what modifications we do to those cells, they'll be closer or further away to the human cells that we're most likely injecting these into. And that's going to determine their efficacy, so their effectiveness. So we can see over here, murine cells from mice, they're going to be very little human, and so actually your body might treat them as antigens rather than antibodies. So it might actually attack and destroy them. Or it could be 100% human. We could grow them in human-based cells, and we could have very low immunogenicity, but obviously it's very dangerous to grow tumorous or cancerous cells inside of people. Anyway, so we can use these antibodies not only to provide the sort of fast action response against an infection of something like rabies, but we can also use it to detect whether or not somebody is pregnant. If you guys remember human chorionic gonadotrophin, which we should have just talked about if you'd watched the 11.4 review video, that's the thing that keeps the corpus luteum alive, which is, remember, that first little organ that's producing the hormones necessary for continued pregnancy. The placenta can develop. But monoclonal antibodies can actually detect the presence of this hormone, and what we do to do this is we basically take the antibody, which is this Y, and we attach it onto an enzyme, and then we actually make the enzyme so that it will change colors when something's attached to the antibody. We then go ahead and take other antibodies and we fix them onto a little dye plate on the pregnancy test. And what will happen is these free antibodies with the enzymes that are floating around, if they come in contact with HGC, they'll change color and get excited, and they'll come down and actually bind onto this fixed antibody. And when that happens, it'll cause a color change in the enzyme that will dye the substrate red. So we can see here it's usually blue. There'll be like a red line if it's positive. Then we have a control site. This is just to let the person using the pregnancy test know that it's still working. So the control site is going to have that same dye substrate that's going to change color. But in this case, it's actually just going to bind onto any of these free enzyme antibodies that are wandering around, just to make sure that these guys are doing their job and the receptors are all working. So a positive pregnancy test is going to have a double solid line because we're going to see these enzyme attached antibodies are going to bind onto HTC and then bind onto these guys and produce some sort of color change, whereas on the control site we'll also get a red line because we're having these enzyme-bound antibodies also bind onto these receptors. So we should get 2 red lines. The negative result is where there's no HTC present, so we won't get this guy, but we will get this guy to show that, yes, the test is still working, but no, there is no HCG present, and therefore no pregnancy. Of course, this doesn't necessarily mean that there is no pregnancy. It just means that there's not enough HCG yet to detect pregnancy. But if it's early enough, you might not actually be able to detect it at all. Which is why it's good to do pregnancy tests after a certain amount of time has passed. Anyway, so hopefully you guys, that clears up the last little bit of topic 11.1 and kind of ties it together with the other topics. It's pretty cool. That's it for topic 11. So look for that. I'll go ahead and post the assessment for it, which will be OpenNote, onto the Google Classroom, and I'll give you guys several days in order to complete that. You can use any of these notes to help with it. I just ask that you don't go outside of the Google Classroom looking for resources unless you're looking at your textbook. Guys, have a great day. Hope you're all staying safe and well. And sadly, I've just learned that I will not be seeing any of you guys again, which is kind of insane. But, you know, like for the end of the year because the schools are closed. But I'm going to, whether or not if I can, I'm going to try to come to the testing sites and just to say hi and, you know, see if I can bring you guys donuts. I don't know if that's going to be allowed because, you know, and also I'll try to, Alyssa, you need to email me so I can know what to bring you so I don't accidentally cause one of these hypersensitive disorders to affect you. Anyway, guys, I'm actually I'm pretty sad I'm not going to be able to see you. I miss you guys, but I'm going to do my best to catch up with you at around exam time. Anyway, stay safe, stay well. Take care.